This week we're talking about global circulations, uh, or we're looking at things in terms of if you averaged weather over a few weeks or a year, what would the planetary circulations average out to be? And or say you changed them with season. But we're looking at things that cover very, very large areas. We're not delving down into, oh, there's a front in my neighborhood or low pressure is moving by. We're going to look at things like monsoons. Monsoons are an atmospheric phenomenon that occurs over a period of weeks, literally months usually. And I've got up right here a precipitation map for the last 24 hours for Arizona. Notice there's been some really significant precipitation, over 2 going on 3 inches of precipitation in some areas in Arizona in the last 24 hours. That is because of the North American monsoon. So if I was to look at a surface map right now, there's nothing down there but high pressure. But because of the way the North American monsoon works, it pulls in moisture into that area during this time of year for the next July and August, starting probably in late June, and it will bring moisture in there. It gets dumped as precipitation. This is the time of year when they get lots of precipitation in Arizona, parts of New Mexico, Mexico. These are all times that are part of the North American monsoon. We'll talk about why that occurs. Another aspect that's going on right now is the Climate Prediction Center. We want to look at global weather. Part of global weather is determined by things like El Nino or La Nina. These are the current sea surface temperatures anomalies. Generally, we look at Nina 3.4 region. It's kind of in the middle of the Pacific. Notice all winter long until April, temperatures averaged about a half a degree Celsius for sea surface temperatures below normal. Now we're almost up to 1.5 degrees Celsius above normal and rising. And you can see it going up everywhere. So this is a significant weather event and has major implications around the globe. So let's talk about these global circulations, what they mean as far as the weather goes. So we're going to start just looking at how things in various parts of the world can impact other parts of the world. For example, and we're going to look at an area right now over in Africa, the Sahel, which is just on the transition between the northern Sahara Desert and the southern areas in Africa. Depending on how that moves, it can create a lot of rain, give wonderful agriculture, or lead to literally starving conditions. So the West African monsoon governs this. Here's that monsoon word again. Here is the region we're talking about. So air moves in from the tropics into this area. And if it comes in enough that year, great rains, good crops, everything's wonderful. If it does not do that, say it stays a little bit further south, then the desert that's just to the north here kind of drifts south. All of a sudden, these people are not getting any food because they're not able to grow any crops. This is a global kind of circulation. We have a rotating Earth. And we said, oh, if we didn't have a rotating Earth, the sun would always point in one spot and the other side would always be dark. So you would have the greatest sunlight coming right in at the equator, especially if it wasn't tilted either. Lots of heating there. We know the air would rise. Coldest on the other side of the world. One big circulation in the northern hemisphere, one big circulation in the southern hemisphere. However, we do have rotation. This begins to turn the winds and moves them. What you wind up with is low pressure near the equator, where the most sun shines, air spreads out the most. So spreading out makes it less dense, lower pressure. But there's another area of high pressure about 30 degrees north, and another area of low pressure, 60 degrees north, and actual high pressure is typically at the northern southern pole. So we wind up then, if you were to look at the globe, you would probably see around 30 degrees north high pressures, and around 60 degrees north lots of low pressures. Now, continents, oceans, break this up a little bit. But here you can look. Here's a wintertime map. Remember, wintertime, the sun is further south, so it's pushing down the low pressures. So instead of being at 60 degrees north, maybe they're at 50 and even 45. That means they're coming in through Alaska, northern United States, out across southern Greenland, and into Europe and all that area. And some will be a little further south and some will be a little north. But if you averaged out, there's a lot of low pressure along that area. Same, a little further south than 30, you are going to have high pressure. So in the summertime, that high pressure builds north over the Atlantic and over the Pacific. The lows a little further north, more up into Canada and across central Greenland. And with that high pressure building in, you wind up with the Bermuda High on the East Coast, which we've had a lot of this year. So all these things interrelate to what we look at as global weather. And here you can see them, how they work with each other. These subtropical anticyclones, when Columbus was trying to sail the world, come to the United States, actually he was trying to go all the way over to India and Asia, but we got in the way. What he looked for was a wind that was blowing from where he was over Spain and Portugal towards the west, or he wanted an east wind. The southern part of these subtropical anticyclones, guess what? Clockwise circulation, they're going to have an east wind. Also, the southern part, a lot of it has, especially on the eastern side of them, they're going to have compressional warming. What does that mean? Well, the eastern part of these highs would be San Diego, for example. The Sahara Desert would be another area. Those areas have that kind of drying in the summertime. Very sunny days, lots and lots of warm weather, not much rain. The western side of the high, think of Charleston, South Carolina. They get lots of rain in the summertime. So these highs control planetary type weather and dictate literally some types of seasonal. Poleward, we have two general areas, the Aleutian low over the North Pacific and the Icelandic low over the North Atlantic. Southern hemisphere, almost a continuous belt of low pressure around Antarctica. Now, these lows push polar fronts north and south, and polar highs come with that as well. We're going to talk a lot more about that. Up on top of the worlds, we have the polar vortex. So these are high-level circulations. They're not down at the surface or whatever, but they get ridiculously cold. And the stronger they are, the colder it may be in the center of that low. But at the same token, none of that air is probably moving south if it's very strong. Think of it as the faster the winds blow, it won't let any of the air out. It just kind of traps it there. So it gets very, very cold, but the air doesn't get down into the United States with that very cold air mass. Now, if it weakens, on the other hand, then the air may move south, and we get some of the coldest weather we get in the winter times when that polar vortex weakens. Intertropical convergence zones occur right where the sun is directly overhead. So that means if you're on the equinox, the sun would be directly overhead at the equator. You're getting the most heating there. That's the hottest place at that time. Air is being pushed upwards. And the winds then move up and down again when you get further into the highs to the north. Further north, we get between that high and the lows to the north, we wind up with the mid-latitudes, where we live, and a bunch of lows and highs move across all the time. They will shift further north in our summertime. They'll move south in the wintertime. These contribute to getting the heat pushed up to the north. Remember, the Earth is always trying to balance its heat. In other words, it is trying to say, hey, I'm too cold up north. I want to make it warmer. So it's always trying to move that warm air up to the north. The tropopause, the top of the troposphere, changes radically as we move from the equator to the poles. In the poles, it's always cold, very dense. Tropopause is fairly low. Down by the equator, the air is hot. Remember, it expands, it's less dense. You're pushing the tropopause higher. In between, where we have these fronts and lows moving by, we have a tropopause that goes up and down depending on where it is in relation to the fronts. The trade winds develop. They're on the south side of the Bermuda High, for example. And when they develop, they can actually suppress the air, descending the air a little bit above the ground. Hawaii is under the trade winds. You would think of Hawaii as being in the tropics with all the moisture, warm oceans around it. But because of the trade winds, they have a stable layer aloft, so they don't have a lot of thunderstorms. They get some rain, significant rainfall, but the clouds never get high enough to produce thunder and lightning. Interesting that way. So the intertropical convergence zone will move with the sun. It's always going to follow the hottest places on the planet. And it's interesting that over the ocean, it doesn't move a whole lot. The ocean has a very high specific heat. We don't cause a lot of temperature change between summer and winter. So the intertropical convergence zone is not going to move a whole lot. Over continents, however, and especially over Asia, look at this. The intertropical convergence zone's well south in the Indian Ocean. And all of a sudden, in the summertime, it's all the way up into the Himalayas. This is because of that intense heating. And with that, it's going to completely change wind circulations. Again, we've talked somewhat about the Charleston and San Diego, the difference on the different side of the highs. These highs are semi-permanent features. They actually impact ocean currents. That wind's constantly blowing in a clockwise circulation around these highs. What's it going to do? It creates a constant flow of ocean currents. Yes, salinity, the haline circulations, all that play a role. But this is the primary driver. So in the Atlantic Ocean, we have high right around 30 degrees north. So along the east coast of the United States, we have the Gulf Stream because that high is pulling air up from the south. And that Gulf Stream is then heading over towards England. It actually keeps England a little bit warmer than it would be otherwise. By the same token, over in Spain and Portugal, water's flowing down from the north, so they're actually a little cooler along the ocean. Think about it, along the west coast of the United States. We all hear about California's ocean being kind of cool, and up over Seattle and Portland, Oregon, and all that area is cooler. It's because of this ocean current coming down the coast there, keeping it cooler. So these reversal of winds are what we're talking about from monsoons. So over in Africa and Asia, India, that monsoon causes tremendous difference in the weather between winter and summer. In the summertime, intertropical convergence zone has moved north. We have lots of moisture coming up out of the Arabian Sea, out of the Indian Ocean, and into that area. Also coming in from the Pacific and all. Lots of rain develops, very heavy rain, sometimes tropical storms even. However, in winter, all the air is flowing out of the continent down across that area. There's no moisture. It's extremely dry and much cooler than you might anticipate. All because of this intertropical convergence zone. That's the monsoon. Monsoon is seasonal circulations. This is not a day-to-day thing. This is over a month or 2 months or 3 months in some cases of how the circulation has changed. And you can see here the graph of the amount of precipitation associated with that at New Delhi. Nothing the rest of the year. Interestingly, we have a monsoon as well in our area. I told you about that one going on in Tucson now. What happens is the mountains, the desert out here get very hot, pulls in air from the east and from the west into that. You get convergence. Oh yeah, the desert being hot means as you go up in the atmosphere, pressure doesn't change as much. Not as fast as if the air was cold. So you wind up with high pressure aloft, pulling in all this moisture from the Gulf of Mexico or the Pacific up the California Gulf there into that area, and you wind up with lots of rain. Once these set up, it can take over a month or more to get rid of it. During that time, some very heavy rainfall could occur. Again, look at Tucson. July, August, over 2 inches of rain. The rest of the year, less than an inch or way down, almost nothing. Okay, Rossby waves. We're going to talk a little bit about, we talked about the waves in the mid-latitudes when you got further north. They occur in both the southern hemisphere and the northern hemisphere. Rossby waves are what we call long waves. They typically, if you looked at a picture of the winds from on top of the poles and looked down, you would see what looks like anywhere from 2 to 5 wavy patterns. There may be little tiny waves inside these, but these are the general waves that are in there. So in other words, think about the ocean. I guess you could argue that there's like one wave and water goes down. Well, there may be a lot of little things in between the two where the one wave and another one comes. Those little extra short waves or whatever can make a difference on how that wave looks, how the Rossby wave changes. And eventually these waves move around the world. With that, they can cause zonal flow or meridional flow. Meridional flow has the deep troughs. In other words, take a trough of cold air pushing down, Rossby wave, we'll say, where it has high pressure over Alaska, low pressure over the central Canada. It is going to think about on the west side of that is very strong north wind. If it's very deep and it pushed all the way down into Texas, for example, that would be a meridional flow. If, on the other hand, it never got anywhere below North Dakota, that would be a zonal flow. It would typically be moving very fast from west to east. The other one would be moving from the northwest to the southeast. They can make dramatic differences in the weather. Right along the zonal flow, you may have very sharp temperature contrast, but maybe a lot of little weak lows. Meridional, even sharper temperature contrast because we're much further south. We pulled all this cold air in out of Canada. We pulled all the moisture and heat up from the Gulf of Mexico, and we wind up with much stronger systems. And here you can see the patterns I was just talking about. We get blocking systems sometimes. If you ever look at a river flowing or a stream and you see where it just kind of goes in a circle for a little while, uh, that's a blocking pattern in the atmosphere. Same thing happens. The atmosphere is a fluid. So you wind up with what we call omega. If you saw this symbol in the Greek alphabet, this looks very much like an omega symbol. Many times we'll get omega blocks in the atmosphere where you have cold air just sitting in one area, warm air in another, and a cold on the other side. And the flow, instead of going, from the west to the east, is just sits in these circles. When that happens, you get extremes. Depending on where you are in this omega block, you can have very hot weather, very dry weather, or very cool, cold, even very wet weather. These are going to lead for record events many times. And here you can see one of these type of events where the block occurred. All right, another aspect of these global polar circulations is the fact that we know the hotter the air, the slower the pressure decreases with height. The colder the air, the faster the pressure decreases. Well, think about along a polar front up in the north. On one side of that front is warmth. Temperature is not cooling off nearly as fast in the vertical. Pressure is going to drop fairly slowly in that vertical. Other side, we have a very strong, tremendous cold air mass. The pressure is going to drop fairly quickly. What you wind up with is a very, very strong pressure gradient, and that's where the jet streams form, right near the tropopause many times. The Coriolis effect will balance these out, but you can see the seasonal shift. The summertime, jet stream tends to be along and up over the Great Lakes or even up into Canada in the wintertime, may come all the way down into Florida. There's also a subtropical jet stream that occurs and sometimes puts surges of moisture into the southern United States. All right, I talked about Rossby waves. Here's a Rossby wave, big wave. Here are little waves in between them, short waves moving along. And with those, you wind up with areas of strong winds producing very strong divergence, and other areas where the wind's lighter, which you wind up with convergence. And where the divergence occurs, you wind up with low pressure tends to form at the surface. Where the convergence occurs, you wind up with higher pressure at the surface. And here you can see a jet streak, and you can see where there's divergence in the left front quad and the right rear quad. And the other two quadrants have convergence. We're going to talk a lot more about these when we talk about our area. I showed you El Nino, what it's doing. What happens when El Nino gets very, very strong? The trade winds weaken. Areas of heavy rain shift from the western into the central and tropical Pacific. So El Nino is the warm phase, La Nina is the cold phase. Typically, you can see here, they alternate. This is for a lot of years. We had a stretch here where we had several years of La Nina, then we had some years of El Nino. But notice, most of them, the worst one was almost 3 degrees Celsius. And that was right around 2012 or so, 2011, I believe. That was an extreme event. Well, we may be approaching that this year. We're moving up into that kind of a range. All right, one final thing here, we'll just talk a little bit about Ekman's spiral. If you go to the coastline, we'll take California as being an obvious choice here. Because of the Coriolis effect, the water moving from the north is going to want to tend to turn to the right. And as it turns to the right, it's going to want to tend to turn to the right more, the lower it goes in the depth. So you basically create a vortex or a circular circulation all the way down to the bottom of the ocean. That pushes in some cold air up, cold water up, and you wind up cooling even more along the coastline because of the Ekman spiral. This occurs along the equator and other areas as well. So we've talked a lot about the El Nino and stuff here. So I'm going to move through this area pretty quickly. We can sense El Nino using various satellite techniques. We also have global monitoring systems out there for now, the ocean. And here are the different regions. Here's Nino 3.4, which is what we use for determining whether you're in an El Nino or La Nina. All right, there's a couple other broad categories. North American oscillation is one. What it is the pressure gradient difference between subtropical high, which we know is around 30 degrees north, the Azores, subpolar low, which is up over Iceland or Greenland. The stronger that variation, the more winds blow. The weaker, the less winds blow. These have a major impact, and they can hang around for a few weeks at a time, especially in the winter, and they can control temperature and precipitation patterns in the eastern half of the United States, Europe, North Africa. The stronger the positive index, the stronger the winds are going to blow. The negative index, the weaker the circulation out there, the less the winds are going to blow. And they have significant differences on how they impact the United States. You can see that here. All right, I talked about the Arctic oscillation earlier and how if it's very, very positive, we don't get a lot of cold air down here. If it's negative, we get a lot more. There's also a Pacific decadal oscillation that occurs as well. All right, finally, MJOs, or Madden Julian oscillations. What happens is areas of thunderstorms develop over the tropical Indian Ocean, and they propagate literally around the globe. They're large areas. They may cover thousands of square miles of thunderstorms. And they will propagate, and what happens is, as they're moving along, there'll be an area of uplift in the air and an area of downlift as they pass. So when these go by, they can cause showers and thunderstorms and literally low pressure to develop, or they can weaken low pressure depending on what part of this circulation they are. We track these around the globe. We didn't know about them until about 30 or 40 years ago. But as we've learned to track them, we can actually see how they relate to developing hurricanes. They can relate to developing low pressure systems because they cover more than just the tropics. They develop in the tropics, but they can spread over a larger area. So it's a lot of information I just packed into this. So I hope you get it. Let me know if you have any questions.